Hello everyone, my name is Gmeiner. I work at the Garcia's graphics team, and today I have the pleasure to give you another etnaviv status update. Usually when I do this kind of talks, I look into the different Git repositories, do a small Git log magic to figure out what was done during the last year. This time I also talk about some interesting work in progress topics. So let's start with the first area of interest, the kernel space. For my personal view, the etnaviv kernel driver is more or less feature complete for the current user space driver. There are some bug fixes, but overall, that's it. There's one interesting patch series. Someone is working on PCI support for the etnaviv kernel driver, as there are some PCI cards in the wild that are using the Vivanti GPUs. And this developer was able to use the patch kernel driver in combination with Mesa to get it up and running on a PCI card. Hopefully this patch series will find its way into the upstream kernel. Let's move on to the user space. In the user space we now have full EtherSpec support, which means decode and encode. There's now a common etna core info struct that lives under source etnaviv common. There is a so-called hardware database that landed, which is more or less a composition of downstream kernel header files from different SOC vendors which are licensed under MIT. Now we have a Rust-based assembler. We finally support MSAA. We support multiple render targets. There are the usual piglet and dbq fixes. Tomeo is working on MPU features. And on the work in progress side of things, I've been working on a new backend compiler that is partially written in Rust, which enables OpenCL support. And also I'm still doing a lot of reverse engineering work. For instance, I started to look into the extended vision instruction set. And yeah, more or less I'm reverse engineering all the missing features that we need on the Mesa side. On CI side, finally CI-tron supports my power delivery unit and the Vivanti GPUs. The Vivanti GPUs are special as you need to query the information like model and revision at runtime, as the device tree does not provide this information. Sadly, my board farm is offline for some weeks now and there is no coverage. But I pulled the trigger to use CI-tron and I hope it is done soon, but there's still a lot of work on the Mesa side to do the switch finally. Also, I got some new shiny hardware that waits to be connected to my CI-tron gateway. At the bottom, you see a screenshot of FreeDesktop's GitLab instance showing my first DAT that is connected to a CI-tron gateway. Wonderful. Thanks for your time. If you like such kind of topics, feel free to join Garcia.
Good afternoon, everyone. I'm Ray from AMD Linux GPU team and work on the AMD GPU kernel driver for many years. And I'm happy to introduce the new topic about the GPU compute virtualization for VirtIO in this year. And yeah. This is our team members, and I'm happy to introduce there are 4 new members: Penny, Lingshan, Trigger and Zhao Wei to join our the virtual GPU support in AMD, and also we get the great support from the demonstration, which from the Kaba. Yeah, thank you. And this is the record for the last year, and we kick off the virtual GPU support for the Zen hypervisor, and we enabled VirtIO and Venus in the first half of last year, and in the second half of this year, we introduced the virtual native context, which leveraged the idea from the Rob. Yeah, and to get the better performance for our GPU virtualization design. And today I would like to introduce a prototype for the MD Rockon and the native for to leverage native context solution. Let's support OpenCL based on the virtual GPU. This is a bit different than the original libdm based graphics design. And what is Rockon? Rockon is an open source software platforms for the compute AI for AMD GPU series, and we have provide multiple interface support for the popular the computer frameworks and the models, and like the TensorFlow and PyTorch, and for the compute ecosystem. And we have a kernel KFD driver and libsync, which is similar with the libdm, and we also have Rockon runtime, which is similar with the Mesa. And based on the Rockon runtime, we have heap and OpenCL runtime, and to inside of the Rockon stack. This is all for the compute stack, and our OpenCL support is over the AMD Rockon on the AMD GPU series. And this is the first the trying for the OpenCL support based on the virtual GPU and the virtualization platforms. And we are you can see we provide AMD Rockon in the host DOM 0, that's based on Zen, and support the OpenCL, native OpenCL over the AMD Rockon on the host. And in the guest, we are using the API forward for the OpenCL API. That is similar with the Venus driver in the Vulkan. And we also leverage the Bob memory, and also add the OpenCL render in the virtual GPU in the virtual render, and to talk with the OpenCL in the guest. You can see we try to add a virtualized VirtIO based on the virtual GPU in the backend in the guest Mesa. But this after we implement the first prototype, we found that it's not very efficiency and the performance is not ideal. So we leverage the idea for the native context in the Rockon as well. So we introduced the libsync, and to forward libsync instead of libdm in the virtual render, and also leverage the virtual GPU Bob memory, the commands in the QEMU, and also implemented the sync capset also in the QEMU as well. Then we can go with the virtual GPU bridge to forward the sync API into the guest, Linux guest. And inside of the Rockon runtime, we also add the virtual GPU in the backend to support the up-level OpenCL driver in like the CL runtime and OpenCL loader, and based on then we can run in the OpenCL applications based on the Ubuntu the DOM-U. And we'll try to upstream the the virtual renders patches at this moment. Yeah, in right now. And this is the comparison between the traditional VirtIO and the OpenCL native context. We can easy to find there is a different. We don't need the OpenCL native OpenCL running in the host side anymore. So we can forward the sunk API from the host to get side directly. Go with the virtual GPU host bridge. Okay, this is the test performance comparison. We are trying to enable the Rockon OpenCL over Rockon with native context approach. We can see the performance for native context is almost the same with the bare metal and the DOM 0. Yeah, it's almost up to the 97%. Yeah, it's the performance is much better than the VirtIO approach. Okay. Actually, we are continue try to upstream the whole solutions. It is ongoing, and we still have some limitations based on our MD KFD driver, and we are trying to support multiple process in the MD KFD for native context as well. And the next step, we also would like to support heap in the MD Rockon stack for virtualization. That means we can support more the leading the AI and the machine learning frameworks over the Rockon for the virtualization and based on the virtual GPU. Yeah. Okay. This is the reference hardware we are working on for to support the whole virtual GPU solution based on Zen. Yeah, you can refer the hardware information directly. Okay, thank you.
So hello everyone, if I haven't met you, my name is Shafer. I'm an engineer with NVIDIA. I primarily work on our Wayland support. Originally, I kind of made this talk so that it would sort of be like an open QA, but we're not doing that today for these lightning talks. So this is mostly about quickly summarizing some things, and then please come up and ask us afterwards. Please come up and ask us tomorrow. So yeah, so to jump right in, this year was pretty big for us. The main thing that landed was explicit sync. That was by far our biggest feature. We shipped a bunch of different implementations of this in our driver for Vulkan, GLX, EGL. We also contributed Mutter and Wayland Linux DRM sync object implementations. We're really happy with how this went, so thank you to everyone who collaborated with us and who we worked with. That went very smoothly from our perspective. And we had a bit of fallout when it first landed, so we worked through some bugs there. We're continuing to look at the last couple remaining issues, but yeah, so far we're pretty pleased with that. We also enabled EGL on Wayland. We've obviously had GLX and Vulkan for a while. So this is clearly another missing piece. And NVFBC, this is the NVIDIA frame buffer capture library. So we have support for that on Wayland. Essentially, this is a fancy way of saying an NVFBC backend for Pipewire. And lastly, just some HDR color accuracy fixes. I mentioned this one because a lot of users have complained about this. There's a lot of like faded color reports. So we're excited that's coming. And yeah, just to quickly summarize some upcoming stuff that's relevant to people here. Our short-term priority is we're ramping up our Wayland testing. We have a lot of X testing, automated or manual. And so we're trying to get to the same level on Wayland. There's some challenges that we face with that I'll mention in a second and that I've talked to some of you about. But yeah, this is our immediate short-term goal because, as I said, we have some gaps there that we've noticed, and so that's really something that's come to our attention. We're also looking to support the upstream color pipeline UAPI. So this does have some limitations that we can't fully expose what our hardware can do. So we're trying to work through that. We're also going to expose HDR vendor properties through DRM. So this might be relevant to compositor developers since that will be available soon. We're also interested in internal display muxing, so please watch the recording of Daniel's talk yesterday about that. that was excellent. The main thing that we have as a takeaway to that is that there's a lot of work to do, especially on the compositor side, especially on the DRM side. So one of the big prerequisites is multi-GPU scanout. So I have a prototype for this that I posted for WL Roots a while back, and I'm hoping to have one from Mutter soon. We're also enabling the FBDev and mode set equals 1 kernel parameters. Mode set equals 1 is necessary for Wayland because it enables like everything you really need in DRM for Wayland. And FBDev is important because that way we're not stomping all over the frame buffer. So FBDev is getting enabled very soon. Mode set equals 1 is taking a little longer, but we've been asked about that, so that's a clear priority for us. And lastly, NVIDIA settings on Wayland, I think, is going to stay read-only. We don't really have a cross-compositor way of doing the configuration that users are accustomed to with X, where they can change displays and do all that. There isn't really a way that we can easily do that cross compositors, and if all that logic is done separately in each compositor, it kind of makes sense that it's configured in the settings per compositor. So we do have some info on it, so you can see info about the graphics card available, you can see some info about power, but we won't have the same level of configuration that you've seen on X. And so really quickly, a couple big things that we've noticed as we ramp up our Wayland testing. We are used to the use case of we need a remote access to a remote machine that's in a different time zone. Maybe it's two engineers handing it off to each other, but really it's that I just get the IP and the SSH login. I can't touch it. I can't have anybody go to it. And that's kind of a problem on Wayland because a lot of the remote desktop solutions kind of assume that you're either there to click, yes, I would like to share my desktop, or it's just fully headless. And we would like for the remote setup to drive the display because we want to test what the users are actually experiencing. We want to drive the display to replicate the bugs that happen when you drive the display. So this one I'm not too worried about. We've talked to some people here, like this is going to come together. We have some short-term solutions, and maybe this is a use case that's unique to us, but hopefully gets reflected. What I'm more interested in is window management controls. We have a lot of automated testing for X where we use something like XDoTool, and there's not really a great counter to that right now in Wayland. So this is really impacting how we can test things. One of the big cases is automated window resizing. So we find a lot of bugs by resizing a window while it's drawing. This exercises a lot of paths in our driver. So we don't really have a great way to do that. Maybe that's just that we're not aware of it. There are some possible solutions. WL Roots and KDE seem to have some support for that. So we're learning how to do this as a company. We're learning how to better test. And if anybody's running into this as well, or if anybody knows something that we don't, please come up and tell us, because that's really something that we need. And lastly, the most important slide is that we would like your feedback. So please come up and tell us what's impacting your experience. Please tell us what features are missing. We are kind of at an interesting point where we're trying to prioritize things that users need and want and developers need and want. So we would like to reflect in our scheduling of what we're working on, because it takes a little while to deliver, things that people actually need and will consume. So obviously there's a bunch of us here at XDC, but also the NVIDIA forums are a good place to report that if you're remote or if you think of something after the conference. So yeah, thanks for your time. That's all I have for this.
Hello, I'm Ricardo from Igalia. I'm going to talk about device-generated commands in Vulkan. This is a new extension that shipped a couple of weeks ago. I wrote CTS for it. I helped with the spec, and I worked with some actual heroes, some of them present in this room, that managed to get this implemented in a driver. Device-generated commands is an extension that allows apps to go one step further in GPU-driven rendering, because it makes it possible to write commands in a storage buffer from the GPU and later execute the contents of the buffer without needing to go through the CPU to record those commands like you normally do with by calling VK-CMD functions. It's like one step ahead of indirect draws and dispatches and one step behind work graphs. Getting away from Vulkan momentarily, if you want to store commands in the storage buffer, and there are many possible ways to do that. A naive approach we can think of is creating the buffer as you see in the slides, which is like we assign a number to each Vulkan command and store it in the buffer. And then depending on the command, more or less data follows. For example, let's take the sequence that is in the slides, where you have one command to push constant, followed by a second command, which is a dispatch. So we can store a token number or a command ID or however you want to call it to represent or to indicate that push constants come. Then we follow this with metadata about the command, which is the section in green color, containing the layout, the stage flags, the offset and size of the push constants. And finally, depending on the size, we store the push constant data properly, which is the section that you can see there in blue, the first chunk in blue. And for the dispatch is similar, only that it doesn't need any metadata because we only want the dispatch dimensions. This is, okay, naive idea. This is not how GPUs work. This is not even how Vulkan works. In Vulkan, we want to be able to process things in parallel. We want to provide as much information as possible beforehand. So this doesn't work. So in Vulkan, things are different. The buffer will not contain an arbitrary sequence of commands where you don't know which one comes next. So what we do is to create something that is called the indirect commands layout. And this is the main concept. So the layout is like a template for a short sequence of commands. And we create this layout using the tokens and the metadata that we saw color red and green in the previous slide. And we specify this layout in advance, and in the buffer, we only store the actual data for each command. And the result is that the buffer does not contain, let's call it the DGC buffer. It's divided into small chunks called sequences in the spec. And the buffer can contain many such sequences, but all of them have to follow this layout that we specify in advance. For example, we have the push constant values of a known size, followed by the dispatch dimension. So it is like that: push constant, dispatch, push constant, dispatch, push constant, dispatch. Okay. And the second thing Vulkan does is to severely limit the selection of available commands. You can't just start render passes or bind descriptor sets or do anything that you can do in a regular command buffer. So you can only do a few things, and they are all in this slide. There's general stuff like push constants, stuff related to graphics like draw commands and binding vertex and index buffers, and stuff to dispatch, compute, ray tracing work, and that's it basically. And moreover, to make things even simpler, each layout must have one token that dispatches work, and which is, I mean, draw, compute, or trace race, but you can only have one of those, and it must be the last one in the sequence. So that makes it even simpler. So something that's optional, not every implementation is going to support this, is being able to switch pipelines or shaders on the fly for each sequence. Summing up, in implementations that do allow you to do this, you have to create something called the indirect execution set, which is like groups or arrays of pipelines that are more or less identical in state, and basically they only differ in the shaders they include. And inside each set, each pipeline gets an index, and you can change the pipeline used for each of the sequences by first specifying the execution set in advance, second, using an execution set token, and then storing the pipeline index in the DGC buffer for each sequence. So a summary of how to use this for anyone trying to find how this works, reading the spec, or interested in implementing this in a driver, is that, well, first you create the commands layout, and optionally you create the indirect execution set if you will switch pipelines and the driver allows you to do that. Then you get a rough idea of the maximum number of sequences that you will run in a single batch, and with that you create a DGC buffer. Then you query the required per-process buffer size, which is, the first time I mentioned that, is an auxiliary buffer that some implementations need to run this, and you allocate both buffers, the DGC buffer and the pre-process buffer. Then you follow by recording the regular command buffer normally, and you specify the state you will use for DGC in advance. This also probably includes some commands that dispatch work that fill the DGC buffer somehow. And finally, you dispatch the indirect work by calling BKCMD execute generated commands. Note that you will need a barrier probably to synchronize the previous writes of the DGC buffer with indirect command reads. And you can also do explicit pre-processing, but I won't go into any detail here. And that's it. Thanks for watching. Thanks Valve for funding a big chunk of the work that involved in shipping this, and thanks anyone who contributed. That's it.
Hello, and welcome to my talk here with this very cryptic title. I think I need to do a bit more explaining about what this is, but first a bit of context about myself. So my name is Philipp. Actually, I'm not working in Linux or Wayland overall. My day job is as a site reliability manager at Google, and we are running Google Cloud authorization, Cloud IAM over there, which is mostly managing and writing documents. So for me, I need to have a bit of coding fun, and for me that also means I'm busy on replacing kind of my old trusty X11 stack, just kind of window maker and so on with up-to-date things, which is basically Wayland. Now I'm trying to do things, and at the moment I'm trying to figure out how to properly deal with surface and input events. So the way I'm reading Wayland, especially it's all very neatly done. It's really focused around surfaces and surfaces getting the input events when basically they're due. So if I think of a reading pointer event, especially Wayland surface like enter and leave interfaces that will indicate for a surface when a pointer enter and exits that. We then get motion events, but only when the pointer is actually over the surface, which is also kind of makes sense for a particular application. And we do not get any information for when the position is outside the surface, which for most applications probably makes sense. And similar also for keyboard, touch events, but also they only get when kind of the surface is active and so on. There is some extensions actually that stretch this a bit and also can give information beyond, but also they're only when the surface has focus. Now, what I'm trying to do is kind of old-fashioned. I copy kind of screenshots of 25-year-old kind of visuals, but also docs, even in macOS, to something similar. Basically, I would like to have a doc for application launches where I can pull in an app and then drag it into the doc. And kind of in the center picture, the doc basically will make space, kind of offer a landing space for what I'm dragging into it. Now, that seems pretty sensible. For this work, however, I will need to get an information of where the pointer is before it enters the dock area. And that is my challenge. So basically what I'm needing is kind of a way for a surface to receive a pointer event also when it does not have focus yet. At the minimum, I would like to have a position of the pointer. I probably wouldn't need buttons. Axis, we can debate. I think we can go without. How? Probably there will need to be an extension of something that gives me that information for each instance of a surface that's mapped, because the surface could be mapped multiple times anywhere. And I would need to get the relative position of the pointer, because also we don't know basically how the surface is laid out overall. Would I need only pointer positions? For my use case right now, yes, but it's also the kind of most obvious thing right now to figure out what the surface may want to react itself to. But there's also touch devices. One could think about other things, but let's not get ahead of ourselves. So that's my challenge. Now, you may be asking, so why do I bring this here? Basically, why don't I just contribute this? And so actually, yes, I'm trying. So there is a merge request that provides us an input observation protocols. Again, that's why the name of the title is this input observation for cases where a surface does not have focus. So contribution is basically up there for Wayland protocols. We'll see how that goes. Fair point, basically, why does this need to be an extension and not just kind of something that is a private extension of what I'm building? Fair point. I think there is usefulness beyond that. So there is accessibility as a case where with that extension and maybe bundled together with a layer extension, but it would be pretty easy to build a tool that kind of highlights the pointer position in a much more obvious way. And as a tool, so kind of it will need to be built compositor specific. It's also possible to think of building tools that would kind of emulate pointer gestures, kind of, again, as a tool that would need to be built into a compositor. Also think like gadgets like Xsize. However, I've been informed that this is actually a terrible example to make my case, so kind of just mention this for completion. Yes, so that it is, but that explains basically when I'm having a talk about input observers beyond surface having focus. And yeah, that's the talk. If you're interested, then I'll be here also tomorrow and happy to hear feedback. And the merge request will also kind of looking forward to get reviews. Thank you.
Hi, everybody. I'm Karol. I want to talk about what I've been done since last year. So I've worked on a couple of drivers. Asahi is officially conformant. I added support for V3D, which is the GPU on the Raspberry Pi 4 and 5. So you already have OpenCL there as well. Accept images, which is a mess to support there. Maybe it counts, maybe it won't. Another driver is Sync, which is also officially conformant. So that's cool as well. I've added support for a couple of features and had also help with other extensions. GL sharing is a big important extensions because some professional video editing tools are requiring it. So that's great to see. Yeah. Then there are a few details I had to work on to support big dispatches. OpenCL doesn't really restrict how big of a compute job you can execute. So if you want to have like billions of threads, then the runtime just has to accept it. The problem is if the hardware can't execute it in one dispatch, then you have to split it up in the runtime. So I've added support for that, which is also required on some SUCs because they can't really dispatch big jobs anyway. Kernel variance is also interesting because the API supports also to add offsets and other things to the invocation ID. So there, usually every kernel has like 40 or 50 instructions, which is just adding and adding with 0 and multiplying by 1. So it's pointless work. So that's a little bit, a little optimization and a lot of core reworks and bug fixing. Those are the extensions I've been working on and haven't finished yet. There's a lot of image stuff, which is optional. Interesting are the bottom two ones. One is the buffer device address extensions, which will be useful for supporting more the open source or cross-vendor HIP implementation, which added support for that, because not every driver actually supports shared virtual memory, and they basically need a pointer or an address for a memory allocation, which OpenCL by default doesn't provide. And I have shared virtual memory implemented on top of Iris and Radeon SI. Yeah, I will talk about it later. So, work in progress by the community. People have talked about it in other talks. There's work in progress for etnaviv and for VirtIO as well. So, shared virtual memory. I have a prototype, and the long didn't read this. It's basically like VM bind, but in Gallium. I have some details. I will create a merge request at some point for this, but basically it allows me to cut out a VM range and then assign addresses to memory allocations. And this will allow me to basically support SVM also across vendors and multiple devices. So yeah, some people were interested in this, and I wanted to implement shared virtual memory anyway. And if you don't know what shared virtual memory is, it's basically you get a pointer and you can use this pointer on all the devices you have in your context and also on the host to access the same logical memory allocation. And the runtime is responsible for synchronization, the content of the actual device local memory allocations. Yeah, that's it.
Yeah, so just again, my name is Austin Shafer. I'm an engineer at NVIDIA who works primarily on our Wayland support. Today, I'd like to talk about Vulkan for Wayland compositors. Specifically, is it the new best choice if you're writing a new compositor from the ground up? So why Vulkan? I'd like to argue that Vulkan's explicit nature has some inherent advantages for compositors that are currently kind of underrated. Because Wayland predates Vulkan, it's kind of just an assumption that if you were writing a compositor, you reach for EGL. The main purpose of this talk is just to say, I think that maybe if you're writing a new compositor, you should really think about reaching for Vulkan first. And so obviously this is aimed at people who can switch graphics APIs in their compositor. I'm not saying that everybody should just rip up all their EGL code that is fully tested and mature and just replace with Vulkan and it'll solve all their problems. What I am targeting is people who are writing new compositors who get to decide, hey, what direction do I want to take this in? Or people who have multiple graphics backends for a compositor who want to decide, hey, we've been prioritizing EGL as the default, but maybe we should be prioritizing Vulkan instead. That's really the goal here, and the goal is to promote discussion. If you've run into similar things, my points are based off of things I've observed while working on multi-GPU features, so maybe other people have seen similar things, maybe you disagree. Really, the goal is discussion. So to dive right in, the thing I'd like to start with is the fact that explicitly creating every property of an image is a big advantage for compositors, specifically because you have more control over how you copy things and the residency and where they are. So VKCMD copy image and blit image perform format conversions, and more importantly, for compositors, they don't need to invoke a full rendering operation. This last point becomes more interesting for cross-vendor copies, because the way this is currently really done in compositors is by essentially rendering to a linear texture and then importing that linear texture on the secondary GPU. So that becomes a problem on certain vendors, primarily NVIDIA, but some other ones who cannot render to linear. And so currently, the best thing to do is just fall back to GL read pixels, which is very expensive. From talking around, and we have some ideas of technically the hardware can render to linear, but you can't attach a depth buffer. So maybe there's some possibility we could do that and try to optimize this case. But on Vulkan, it's really easy. You just do a VKCMD copy image and you're done. Comparatively, it's much nicer. And because all the images contain details of the tiling, the layout, which GPU they're on, it all just kind of works like you'd expect. The next major advantage, I'd say, is the fact that devices are a top-level object. All device-level functions except a VK device is the first parameter. The immediate impact for compositors here is that you don't have to manage which EGL context is current right now. This is also really specific to multi-GPU and really hits you hard there, because as you do those copies, you have to switch context. There's no other way to do it. You have to switch, and depending on how your compositor is written, you might have, oh, I need to switch the current context here, but it was set 5 functions above, and I need to track saving and restoring it. There's possibility for bugs there that's kind of annoying to deal with. On Vulkan, you don't have that because you're just calling a function with a VK device and you're done. Also, because VK allocate memory is a device level function, it means that you fully know where all of your memory is resident. You're allocating from a specific heap on a specific device. You know exactly what's happening, and there's no questions there at all. I'm not convinced that this is a huge advantage as is. I mean, the make current advantage is real, but I think it's more interesting for what we can potentially do with Vulkan because it does these things. Can we ask ourselves cool and interesting questions that we can't with EGL because we don't have those devices as exposed to the same degree? So things like device groups, presenting to multiple devices as if they were one logical device. What does that look like? How does it impact compositors? What about multi-vendor device groups? Is that a thing we could explore? Right now on EGL, if you want to allocate scan-out buffers, you have to use GBM. On Vulkan, we could add this as an image usage, although it might be tricky. We might have to see if a particular swap chain can scan out a particular piece of memory. EGL sort of has this with a vendor-specific function or a vendor-specific extension, but it hasn't really caught on, so maybe there's also some advancement there we could do. And lastly, cross-GPU copies in one API call, essentially a VKCMD copy image with 2 VK devices and 2 VK images. I'm not personally convinced that this exists or should exist in a graphics API. I think it's something that the app could control, but you know, these are the types of things we get to ask ourselves, and we have the possibility of exploring because of how Vulkan is. And lastly, just some miscellaneous points. I don't think these really move the needle, but I think that they're interesting to mention nonetheless. Everything in Vulkan is extremely explicit, including the synchronization and memory model. You can go look up the interactions for every little thing. The documentation is incredible and very specific, so that's also an advantage. This means that because it's explicit, you don't have to rely on implicit sync for synchronizing presentation operations and such. And on vendors that don't support it, you don't have to use a GL finish all over the place, hurting performance. There's also fine-grained work submission. On EGL, you just do a EGL create sync, which just synchronizes everything up to that point in the command stream. On Vulkan, you can have much more control over tying signaling operations to specific things within command buffers or specific command buffers. Validation layers are also pretty cool. They catch lots of API usage bugs, so that's a new thing that you get with Vulkan. And also, timeline semaphores are really interesting, and I think maybe could have some cool implications for explicit sync in compositors. Like, for example, could we turn a DRM timeline sync object into a Vulkan timeline semaphore? Maybe there's some spec expansion we can do there. So yeah, that's all I have for today. Yeah, thanks for your time.
Hi, I'm Thomas, and this is a project I did to kind of scratch an itch I had myself when implementing some Vulkan extensions and drivers. The problem is that, well, we kind of have the CTS that we can always go in and implement against, but it's also nice to know what games are actually using this extension so that you can go in and smoke test, kind of see that you get things right and it's performing. And the problem is that I don't think there is such a list, and the way I go about it is to just ask to see if people kind of have a mental list in their head of like what games might be relevant for this extension. And even then, when you have that game, you don't really know where specifically in the game the extension is used. It might be in the intro scene or in the menus, or it could be that it's only used in the final boss scene. So you kind of have to play the full game to actually test it. So it's yeah, it can be better. Also, there's a lot of games. I don't know if there's 100,000 games. That's just a number I came up with. But it's more games than I have time to like scan and write a list for myself. So I kind of have to, if I want to get this complete list, I have to engage with the community and get a lot of people to help. So I'm trying to find a way to make it easy to compile this list. The idea was that I would write a Vulkan layer that you would basically just put in between the game and the driver, and then you would kind of intersect all the function calls and figure out like, hey, right now the game is actually using this extension, right? And you can use it on like complete drivers, so you could use the NVIDIA driver, and yeah, that probably has everything implemented, so you can just kind of use that if you have this Vulkan layer. And yeah, it has to be easy for normal non-programming users to use. So it would be good to kind of just give them that and say, hey, go play games with this, and then hopefully find a way to make it easy to submit the results. The status is that it's still a work in progress. Right now, it detects 145 different extensions. It simply just prints the extension name to the standard out when it detects that it's being used. So that can be improved. I wanted to publish the code, but I didn't bring my SSH key, so it'll come when I get back to my computer. I'll send in a merge request for it. Yeah, I wanted to do an interactive demo where you could kind of see that while you are playing the game, you reach a new area and it pops up with new extension names. But yeah, you'll just have to live with the the static image. It's a game I really like to test on. Transport Fever it uses native Vulkan, so that's cool, and it has some really nice music. So I like to play with that one. So basically, I'm playing the game, and in my console, it's writing out the extensions as I start using them. That's not ideal for logging when exactly you use the extensions, because you're probably playing full screen. So the future work, well, yeah, 145 is not nearly all, so there's a lot more to do. I also kind of want to show the extensions in like an overlay on top of the game. And then I need to figure out like, how do I get users to submit this stuff? I haven't even thought about that, and I haven't thought about how to present it either. Like maybe just in a GitLab repo or something where you can just get the list. I don't know. If you already have this mental list of like, I know this extension is being used by these games, then I would love to hear about it, because that could help me when implementing it to kind of check that, hey, I'm actually catching the right stuff. So if you have that, send me an email or catch me on IRC if you're in the same channel. So yeah, that's all.
Hello, everybody. My name is Rodrigo Siqueira. I work at AMD in the display team, and today I want to point some directions when you need to debug a display issue. So since we just have a few minutes, let's start. And I guess the first place that we can start is a DCN overview. DCN stands for Display Core Next. And if you want to learn more, please check the documentation. You can see the link here. But from this picture, what I want to give you the idea is DCN is a highly configurable block, and every DCN version has some difference, but this is an overview of how they usually looks like. So again, more details in the documentation. From the driver organization perspective, you can start to take a look to something like dc.h in the DC folder. Everything here is from AMD GPU folder and the display folder. And we have some generic components. For example, we have core and link. Those are used for most of the DCN. It's going to have code there from there. Then we start to have some more specific code under blocks like hardware sequence, where we're going to have like a common sequence for hardware configuration. And then we're going to have the low-level configuration, which means every hardware that we have is going to have their own registers and some details, and that this is the low level of our driver. And we have a firmware, which is the DMUB, which also we have a block in our driver. So when you look at the code, probably this organization can give you an overview of the issue. But yeah, let's say you have something and you want to start to debug before you go to narrow down things. I guess we can start always from our good friend, the mask. We can check for this display core information in the log. If you see it, it means display is up. We have two information here that they are very important, which is the core version and also the DCN version. I will go back to those later, but let's just move on. Another important information here is when we usually load AMD GPU, we have different blocks. We call it IP blocks. And the one that it's associated with display is this one with DM in the name. And notice that every time we load it, we have a different number associated with it. So this is dynamic, so you need to load and see one. Here in our example is number 5. And let's say you are not sure if it's display issue or maybe another component issue. You can start your debugging by basically disabling it. You just need to do this bitwise operation that where you're going to get the ID number and this basic math, get this value and set it in the IP block mask. You can do it like before you load your kernel, like whatever you prefer. And if you see the issue after disable display, for example, probably it's not a display issue, some other place that you probably want to check. Yeah, this is the first thing that you can try to rule out from the equation. Another thing that you can check is sometimes we see some issue in the display and we automatically think, oh, it's a display issue, but may not be true. One quick check, you can try to take a screenshot or video capture. If you see the issue in the video capture, maybe it's worth to check the user space a little bit more. But if you don't see it there, you probably want to keep going the kernel side. And at this point, you probably want to check if there is an issue in our GitLab. If there is something there, please comment on there. If not, open a bug report in our CI. We have a template, in our public bug report. We have a template for it, so just follow it, and then we can try to help there. And then you open the ticket, and now you want to narrow down by yourself a little bit more. You can go back to the mask, check those two information, the DC version and the DCN. So the DC version is something that can be helpful if you need to bisect, because every DC version has a lot of, when we merge it, which is in a weekly base almost, we also have a lot of specific tests before we merge it. So maybe it's worth to roll back to some old DC version, see if the issue is there. If it's not, you know you need to bisect from one version to another. So the commit looks like this DRM, DM display. And the second information here that it's good, it's the DCN version. We have a lot of different DCN versions based on the hardware that you have. This information you can use to navigate in our code. For example, you can go to the clock information and see if there is a DCN that information. You can go there, like our DML folder, so you know how to narrow down your search in the code. We also have some options for debugging it like in a real time. For example, we have a lot of events. You can probably want to take a look there. Like you can collect cursor information in real time, FPU and other things. We have this other log, which is DTN. This is also have information, for example, pipe split, or if some DCC is enabled, if we have underflow, and many other informations there. This is another very good source of information for the bug. And we also have this amazing tool named UMR. From it, you can basically collect information from our driver, like versions, but you can also get information from registers in a real time, as you can see here, like tracking DCC, and you can also change your registers values. You can also follow the power consumption. You can also see the KMS configuration in a real time, so quite useful. And sometimes you have specific debugs, because in the display we have a lot of different features, and some issues might be caused for one feature or another. For example, we have this pipe split, where basically we have it's a configuration in our descent. Again, check the documentation. This is used for things like video MPO, for power optimization reasons. So anyway, the idea is maybe you have some issue related with pipe split and you want to check things like that. You can enable this debug FS option that you can see here in the slide, AMD GPU DM visual confirm. It will give you a bar at the bottom of the screen. The color indicate like the format, and the size also has specific information. We have more details about this in the kernel doc. It's also worth to check. But you can also have issues like horizontal glitch, which can be caused by many things. For example, if you have a high resolution display with a little bit weird, or you have multiple displays, you might have some flicker. One thing that you can try is basically set the DPM level too high. It means your GPU will use a lot of power, but at least if it fixes the issue, we know probably we need to debug the power issue, or maybe it's a DPM transition issue in the display. We have more information of this, again, in the documentation. If you did that and the issue is still there, maybe it's something specific. We have this struct in our code named DC debug options. You can enable and disable some specific features. For example, for horizontal glitch, you can try to disable this sub VP feature and see if it fixes the issue or not. So this is another good way to narrow down the issue. And of course, we have IGT. I know in the past we have a lot of issues with IGT. It was not that great, but believe me, now it's really good. It's part of our CI. If you can see that you can reproduce it with IGT, it's also going to make our life even easier. Finally, if you are interested on that and want to contribute more, we have also a to-do list in the kernel doc. So please feel free to send contributions. Thank you.
So, hi, everyone. Welcome to my talk. So I'm Frederic Plourde, XR lead at Collabora, and Kronos OpenXR outreach officer. I'll be giving this really tiny presentation about the current status of DRM Lease on the Wayland, but from Monado's perspective, right, super tiny. It's actually just an excuse to close an graphics conference with an XR topic, right, and related to plug Monado, the OpenXR runtime. So we've had DRM Lease on Wayland for 3 years. Everybody loves it. It works great, but there's still some open questions. And that question, for example, here, like when it comes to offering DRM leases, what DRM outputs should a composer, Wayland compositor pick? And there's kind of 3 general approach generated to that. So from the Wayland compositor, you could just offer like leases for all the available DRM outputs. It can restrict that list to probably just the one with the non-desktop flag set. Or it can offer no leases at all, right? And just let the users opt in using whatever means, just maybe naming the connectors from an external point of view. And so here are two scenarios that we faced. So we had 2 or 3 months ago, I think, some fixes, some issues on the Monado side of things. And so here, and this allowed us to interact with the very nice people at Sway and the very nice people at Lab Wayland Compositor. And here you can see on one end of the spectrum, so some compositors like Sway will take the non-desktop flag into account. And so here, for example, we'll serve or we'll offer output number 2 with the non-desktop flag equals true. But from the Monado perspective, this is not always the ideal scenario because, for example, like super new XRX headset, they're not going to be supported by the kernel, and the non-desktop flag is not going to be properly handled. So, here, for example, the XR headset, interesting for Monado would be output number 1, and we missed that. And so, dear colleague of mine, Simon Zenny from Collabora, very recently just introduced in Sway, introduced output leasing commands. Super simple and easy way from a user, from an external point of view, to just output command leasing and choose whatever output it wants for leasing. And so this works beautifully. And this is not available still under discussions, but you can take a look at the pull request in the link down there. On the other end of the spectrums, you find all of those compositors, for example, here like Lab, which are just not going to care, right? They're just going to just offer all the ARM outputs for lease, and then you get to pick, you get to choose whatever works for you. And we had an issue, like this is like kind of the ideal case from the XR compositor point of view, because you can choose and make your own decisions, right? But even then, we had troubles like 2 or 3 months ago with Monado. Monado would just very dumbly pick the first item in the list. And in that case, let's pretend our XR desktop, XR display is number 2. Well, we were obviously picking the wrong one, and many users reported such issues that, hey, my monitor is being picked as the direct mode XR device. And so again, Simon Zenny from my team just had a very quick workaround. So we had that in Monado right now. So I had the ability to choose what is the running connector that we're going to work with via an environment variable. The code has been merged not so long ago. You can take a look at the merge request, and it is there for you to enjoy. Now, before we almost part, related to that work that I just mentioned, so there's, very interesting enough, some movement. There's been some movements in the DRM Lease protocol lately, especially about the withdrawn event. So what happened there is so for those of you who don't know the withdrawn event, so when you're a compositor and you're actually offering leases, so when a connector is not available anymore for lease, you can just send the withdrawn event, right? You're withdrawing the offer. And so in that case, we see that the compositors are encouraged, in bold, right? The compositors are encouraged to send this event when, for example, when the connector gets leased to a client. And so in that case, Monado is really dumbly just like taking a hold in the lease and then just receiving from, in this case, it was Neri compositor, just being served okay, well, that connector is not available anymore for lease, and just releasing it and killing the connector. So we fixed that, but it kind of let us uncover like kind of an undefinition in that spec. And so same contributor of mine, we worked at maybe perfecting how it's explained, so that we avoid this kind of situation. And so now we have that new little bit in the withdrawn event spec. So if a client holds a lease to the connector, the status of that lease remains the same, right? Whether or not you receive that event. And so thanks to Daniel Stone. Where's Daniel Stone? There. So I think you merged that like 4 or 5 days ago. So this is pretty recent changes in the Wayland protocol. And so what's next for us on the Monado side? Well, yeah, in line with everything that I just said, so we'd like to complement the non-desktop flag logic, probably by leveraging libdisplay or something like that, just to be able to deal better with the EDID and make better and smarter choice. And so if you're interested in all that, about the XR aspect of graphics, come talk to me, any of us in Monado, and it'll be a pleasure to follow up with you guys. Thanks.